Imagine holding a weapon made from a metal that didn't come from any mine on Earth. It fell from space. To us, that sounds like science fiction. But more than 3,000 years ago, an Egyptian pharaoh was buried with a dagger made from iron delivered by a meteorite. The blade was rare, mysterious, and incredibly valuable. But here's the strange part. The people who made it didn't know what iron was. They didn't understand chemical elements. They couldn't explain why this metal was different, and they had no reliable way to make more of it. For centuries, humans could shape iron from the sky, but they couldn't unlock the enormous supply hidden beneath their feet. Then, somehow, that changed. Ancient metalworkers learned to pull iron from ordinary-looking rocks. They discovered how to make it harder. They turned it into tools, armor, and weapons. And eventually, this difficult, stubborn metal helped reshape entire civilizations. But iron didn't immediately replace bronze because it was better. In fact, early iron was often worse. So why did it take over the ancient world? The real answer involves meteorites, collapsing empires, broken trade routes, accidental experiments, and generations of craftspeople who understood what worked long before anyone understood why. This is the story of how humans mastered iron. To understand why iron mattered, we first need to understand the world that came before it. For thousands of years, bronze was the superstar of metalworking. Bronze is usually created by combining copper with tin. Compared with pure copper, it's harder, stronger, and much more useful for making sharp tools and reliable weapons. Bronze could become an axe, a farming tool, a spearhead, or a sword. And the civilizations that controlled bronze production gained a serious advantage. But bronze had a weakness. Copper was available in many places. Tin wasn't. Major Bronze Age societies often depended on long trade routes to obtain it. Ships and caravans carried raw materials across enormous distances before metalworkers could combine them inside their workshops. That meant a bronze sword wasn't just the product of one talented smith. It was the final result of an international system. Miners, merchants, sailors, rulers, and craftspeople all had to cooperate. If even one important part of that system failed, bronze production could suffer. For a long time, though, the system worked. Then the ancient world discovered a metal that needed no tin at all. Humans didn't begin their relationship with iron by digging it out of the ground. They found it inside meteorites. Most iron on Earth doesn't exist as clean, usable metal. It's chemically bonded with other elements inside ores. Separating it requires heat, fuel, and a carefully controlled furnace. Meteorite iron is different. Some meteorites contain a natural mixture of iron and nickel. The metal has already formed, so an ancient craftsperson could shape it by repeatedly heating and hammering it. It wasn't easy, but it was possible. Long before the official beginning of the Iron Age, ancient people were already making small objects from this celestial material. In Egypt, researchers identified tiny iron beads dating to more than 5,000 years ago. The beads had been hammered into shape and placed inside burials. They weren't farming tools. They weren't everyday knives. They were decorations. At that time, iron's greatest value wasn't practical. It was rare, beautiful, and connected to something deeply mysterious: the sky. Ancient cultures even used language that associated iron with heaven. And honestly, that makes perfect sense. If the only pieces of metal you knew came from rocks that fell through the sky in fire, you probably wouldn't treat them like ordinary material. You'd treat them like gifts from another world. One of the most famous examples was discovered in the tomb of Tutankhamun. The young Egyptian pharaoh was buried during the 14th century BCE, with gold, jewelry, furniture, weapons, and countless objects prepared for the afterlife. Among those treasures was a beautifully crafted dagger. Its blade was made from iron. Modern analysis found enough nickel in the blade to support an extraordinary conclusion. The metal had come from a meteorite. Think about what that means. Egyptian craftspeople were already experts in gold, copper, and bronze, yet meteoritic iron was special enough to be placed beside a king. But there was one major problem. Meteorites are rare. A civilization couldn't equip thousands of soldiers with weapons made from metal that occasionally fell out of the sky. If iron was ever going to change the world, humans needed to produce it from terrestrial ore, and that was much harder. Copper and tin could be worked using technologies that ancient people had already developed. Iron demanded something new. Iron ore had to be heated in a furnace with charcoal, while airflow was carefully controlled. The process needed to create the right temperature and chemical environment to separate iron from oxygen. Even then, ancient furnaces usually couldn't completely melt the iron. Instead, the furnace produced a rough, spongy lump called a bloom. A fresh iron bloom wasn't a perfect metal bar. It contained unwanted material called slag. The smith had to heat the bloom again, hammer it, fold it, and force out as much slag as possible. It was exhausting work. The result could also be unpredictable. One batch might produce usable iron, another might fail. Even two pieces from the same furnace could behave differently. So how did anyone discover this process? Nobody left us a written instruction manual from the first successful experiment, but archaeology gives us a reasonable possibility. Iron smelting may have grown out of earlier metalworking by accident. Ancient copper workers sometimes encountered iron-rich minerals. Those minerals could enter a furnace as part of an ore, or be deliberately added to help separate waste from useful metal. Under the right conditions, a very hot charcoal furnace might reduce small amounts of iron. Imagine workers cleaning the furnace after a copper smelting session. Most of what they find looks like useless slag, but inside it are tiny metallic pieces that don't look like copper. Someone picks one up. Someone heats it. Someone hits it with a hammer, and instead of breaking like a rock, it bends. That discovery probably didn't immediately create an Iron Age. Early metalworkers may not have known which exact combination of ore, charcoal, heat, and airflow had produced the result. But craftspeople notice patterns. A hotter furnace creates more of the strange metal. A particular rock works better than another. Extra charcoal changes the final product. Different hammering techniques improve its strength. One experiment becomes 10. 10 become hundreds. Useful observations pass from expert to apprentice, and eventually, an accident becomes a repeatable process. There may never have been one inventor of iron. Its discovery was probably a long conversation between humans, fire, stone, and failure. For many years, a popular historical story gave the Hittites of Anatolia a starring role. The Hittite Empire became associated with early ironworking, and surviving records show that iron was considered valuable. Because of this, the Hittites were sometimes described as the people who invented iron smelting and protected it as a military secret. The reality is more complicated. The Hittites were certainly important to the development and spread of ironworking in the ancient Near East, but evidence from other regions suggests that iron technology may not have had a single birthplace. Archaeologists have investigated early smelting traditions in different parts of Africa. Some proposed dates are debated, and not every site is interpreted in the same way. Still, African furnaces and production methods show distinctive features. That raises an exciting possibility. Different communities may have independently discovered how to produce iron. This wouldn't be unusual in human history. When separate societies have access to similar materials and face similar problems, they can sometimes arrive at similar solutions. Ironworking may not be the story of one brilliant civilization teaching everybody else. It may be the story of several groups learning how to control the same difficult material in their own ways. Knowing how to make iron is one thing. Depending on it is another. Iron began spreading more widely around the end of the Bronze Age, during one of the ancient world's most dramatic periods of disruption. Around 1200 BCE, several powerful societies in the eastern Mediterranean experienced destruction, political instability, population movement, and economic decline. Cities were abandoned or burned. Kingdoms weakened. Writing disappeared from some regions. Long-distance trade became less reliable. Historians still debate exactly what caused the crisis. There probably wasn't one simple explanation. Drought, famine, warfare, rebellion, migration, and the failure of interconnected political systems may all have contributed. Whatever the exact combination was, the result was devastating for bronze. Remember, bronze production depended on copper and tin. If ships stopped sailing, roads became dangerous, and trading partners disappeared, obtaining tin became extremely difficult. Iron offered something bronze couldn't: local availability. Iron ore is widespread. A community that lost access to imported tin might still find iron-bearing rock nearby. Iron didn't win simply because it was an amazing metal. It also won because the world that supported bronze was breaking down. Here's another twist. Early iron wasn't automatically stronger than bronze. Relatively pure iron can be soft. A poorly made iron blade might bend or lose its edge. A skilled bronze worker could produce a weapon that performed better than a badly made iron one. So the first major advantage of iron wasn't always quality. It was access. Once people had the necessary knowledge, iron could be produced in places that weren't connected to distant tin suppliers. Over time, however, smiths discovered ways to improve it. The most important improvement involved carbon. When iron was heated in a charcoal-rich environment, it could absorb small amounts of carbon. With the right amount, the metal became steel. It was harder, it held a sharper edge, and it could outperform both soft iron and bronze. Ancient smiths didn't understand the atoms involved. They couldn't see carbon moving into the metal, but they could see the results. They learned which colors indicated the right temperature. They learned how long the metal should remain in the fire. They learned that changing the fuel, airflow, or hammering process changed the blade. Their workshop became a laboratory. Their eyes became measuring instruments, and experience became their science. Then came another crucial technique: quenching. A smith would heat a piece of steel and rapidly cool it, often in water or oil. Under the right conditions, this could make the metal dramatically harder. The first discovery may have been accidental. Maybe a hot tool fell into water. Maybe someone cooled a blade quickly to save time. Maybe different workshops discovered the effect independently. However it happened, the result was impossible to ignore. A quenched blade behaved differently. But harder didn't always mean better. If steel became too hard, it could also become brittle. A sword that held a sharp edge but shattered during battle wasn't very useful. Smiths eventually developed tempering techniques that balanced hardness with flexibility. Once again, they didn't understand the microscopic crystal structures changing inside the metal. They simply knew the recipe. Heat it to this color. Cool it this way. Reheat it carefully. Watch. Listen. Test. Repeat. This knowledge wasn't discovered in a single afternoon. It was built over generations, with every craftsperson adding another small piece to the puzzle. Iron is often discussed in terms of swords and armies. And yes, iron weapons mattered. Large states could produce spearheads, arrowheads, armor, and tools in greater numbers when the raw material was locally available. Empires such as Assyria became famous for organized armies that made extensive use of iron. But iron's quieter effects may have been even more important. An iron axe could clear woodland. An iron plow component could help farmers work difficult soil. Iron chisels could shape wood and stone. Iron nails and fittings could strengthen construction. These weren't glamorous objects. Nobody wrote heroic poems about a better farming tool, but stronger tools helped communities produce more food, build more efficiently, and expand into new environments. Iron didn't just help rulers conquer land, it helped ordinary people transform it. This may be iron's greatest historical achievement. It became ordinary. Meteoritic iron had once been fit for kings. A tiny piece could be worn as jewelry or placed inside a royal tomb. But after humans learned to smelt ore, remove slag, add carbon, quench steel, and control its properties, iron moved out of palaces and into fields, workshops, homes, and armies. The metal from heaven became the metal of everyday life. And that transformation didn't happen because one person suddenly understood everything. It happened because countless people noticed small details. A furnace that burned a little hotter, a rock that produced a better bloom, a blade that hardened after entering water, a tool that improved after being reheated. Most of their names are gone. Their experiments aren't recorded. But their knowledge survived inside the objects they created and the techniques they passed forward. So why did iron replace bronze? Not because the first iron tools were always better, not because one empire instantly discovered a perfect secret, and not because technological progress moves in a clean, straight line. Iron succeeded because its ore was widely available. It became essential when trade systems failed. And generation after generation of smiths slowly learned how to transform a frustrating lump of metal into reliable steel. The story began with rare fragments falling from space. It continued in smoky furnaces, where workers experimented without understanding the chemistry. And it ended with a material common enough to reshape warfare, farming, construction, and daily life across much of the world. Those ancient smiths couldn't explain carbon diffusion or crystal structures. They didn't need to. They knew the most important thing. They knew what worked. And sometimes that's how humanity changes the world. Not with one perfect moment of genius, but with curiosity, mistakes, and thousands of people refusing to stop experimenting.